Hey guys, I hope you are staying safe, enjoying the weekend, and thinking about a lot of science. I am going to be creating a few videos for you on our energy unit. My hope is that I would have all of the lectures done on video so you could go back to them and you could review them, or you could just fast forward them if you think that this is way too simple. So I wanted to start by giving you guys a little overview of where we're going, what we've done so far. The topic is the conservation of energy, and we looked at last class, if there's an external force, then we are using this working energy principle to analyze the situation at hand, where we said that work is energy, or energy can be converted into work. The two are somewhat synonymous, and I did not show this last time, but this is a helpful way to look at the work done in a situation. Remember that work is the force exerted, and maybe it's best for me to get this down too, that work is force times the distance parallel of that force. And we can represent this in graphical terms, where we have force on the y-axis, the displacement in the x, and the area underneath the graph would be the work done, and that's measured in joules. There's several different types of energy that work could then be stored into. We might have work being converted into kinetic energy, potential energy, elastic and internal. These are the four that we're primarily going to focus on during this unit and pretty much for this course. Kinetic energy being that of motion, potential energy being that, specifically gravitational potential energy, being that associated with raising something to a certain height. Elastic energy has to do with if you're stretching out a spring, there's some energy there. And internal energy, I didn't talk at all about this last time, there's energy associated with the molecular motion inside of an object. So if you heat something up, you're getting those molecules to bounce around more vigorously, so there's more energy stored in the object there. The other three that should be listed, but we won't really dive into right now: magnetic, electrostatic, and nuclear, such as like keeping two positively charged protons together. There's some energy in that. So we'll use the conservation of energy to, or as a powerful tool for mechanics problem solving. We can sort of take a step away from the kinematic problem or kinematic gems in the free body diagram, which is complex in itself, and you'll see some simpler problem solving methods. We'll look at it qualitatively with an LOL diagram, and we can do it quantitatively with an energy initial plus the work equals energy final. But if we choose our system correctly, then there shouldn't be any work on the system, so our energy initial should equal our energy final. Thus we have the beautiful conservation of energy. Stay tuned.